The following tools or tutorial will be an introduction to tools you can use to model the flow of water across a surface. So these tools need an elevation to begin, but they're not in the surface dataset. They're aptly named up in the hydrology dataset. We're going to focus really today on flow direction and accumulation, but a couple others that could be interesting. Basin, be able to delineate drainage basins. I don't love this as a tool. I would probably use watershed if I were you. Watershed gives you a little bit more control because you can actually determine the pour points. You can say, look, I'm interested in finding the drainage basins for these major creeks or for all of these streams or so on and so forth, rather than just look at my elevation layer and determine every drainage basin, because it'll find you some really, really tiny ones that aren't too of interest to you. You can also use some of the outputs that we have here to define the order and the linkage systems of streams, which is kind of great. But really what we're going to focus on here is these three. So flow direction's the most important tool in this data set, but it doesn't really have any value on its own, right? The whole purpose of flow direction is to create something that will be an input to everything else, right? It's almost, in a weird way, its own version of the network database from ArcGIS Vector, right, of Network Analyst. You're taking a road layer and you're converting a new data type, a network data set, and that network data set feeds other analyses, right? Even though you may have all of the information that you need on the elevation layer or the road layer in that previous example, you need it to be configured in such a way that it can be easy as an input of analysis for some other tools. That's what flow direction is going to do, right? It's going to take the input elevation and it's going to output something that tells you the direction in which your data tends to flow, right? Flow all cells outward. I'm just saying at the end of my analysis window, just flow everything out. And so it'll take its moment. It's going to produce something that initially seems confusing, but let me just run through it. Notice that there's 8 values. Essentially what this means is 1, I flow east. 2, I flow southeast. 4, I flow south. 8, I flow southwest. 16, I flow west. 32, I flow northwest. 64, I flow north. And 128, I flow northeast, right? You don't have to take my word for it, of course. You can go check. And we'll go to ArcGIS and we'll try to find ArcGIS, flow direction. Right, if you ever look at these values and find yourself really annoyed and stressed out, this is what is being calculated here. And it's eventually looking at the downward slope direction and it's categorizing something based on, right, my value is going to become one of these based upon which cell I would flow into given, right, a surface of elevation. Right, that's essentially what this is calculating itself as right here. Cool? So you've got your flow direction. So the primary one we're going to focus on is flow accumulation. So the purpose of flow accumulation is, given a direction raster, which essentially tells each cell what they should flow into, accumulation is going to imagine, well, what if we did flow? Like, what if one raindrop, for example, or as many raindrops as you want, actually fell everywhere? Where would they all theoretically wind up, right? So this is what's going to allow you to do a first step into delineating stream channels. All right, so we'll do FA for flow accumulation. I'm going to make it an integer just in case if we want to look at the attribute table. So input weight raster is very cool. Like right now, it's just going to imagine that every single cell has a value of 1. And every cell is going to take that value of 1 and they're going to try to flow that value of 1 as far as it can go. And anytime that 2 values of 1 accumulate, they become 2. And anytime a cell that has 2 meets a cell that has 12, it would become 14. And so on until there's going to start to be some cells that have a value of thousands, right? Because 1,000 different droplets would meet there based on the way that things would have to drain. A weight raster would allow you to throw something on top of it, like maybe you interpolated annual rainfall, based on some access to some rain monitoring stations you have. And then that would be different depending on where you were, and then you could actually try to model what the average, right, drainage of rainfall would be, right, based on where areas get a lot of rain versus what areas get a limited amount of rain. You could maybe even do the same thing with, like, imagining it was a torrential downpour, right? Use a lot of rain and see what areas are really susceptible to flooding. So we'll run it. This is going to be one of those instances in which the first thing that ArcGIS returns to you is not going to be the most attractive and helpful, so we're going to have to play around with it to really highlight what we're looking at. And so it kind of looks like a lightning bolt here, but let's mess with the symbology a little bit. Right, again, every cell is now reporting the number of cells that have flown into it. So we can start to delineate things. Let's say that if you are below 100, you don't show up. And if you're above 10,000, then you're just this solid brown. Now we start to zoom in and we can see what we've essentially created. We've defined stream channels. Mini ones that maybe only emerge with a couple of little water droplets flowing down, into ones that are maybe dry streams but miniature streams during the wetlands area or during the wet season, that flow into major stream channels that converge with other major stream channels, so on until they flow outward into the Susquehanna River at various points. Cool little trick here, right? If this is my analytical layer, right, this is actually my stream channel that I might use for other tools such as delineating watershed, for defining stream orders and so on and so forth. I can actually make this a little bit easier to see on a map by using focal statistics. Right, we looked at focal statistics previously as an analytical tool, but it has a couple of visual cosmetic uses too. So in this instance, I'm taking, right, because the reason we can't see this very well is raster doesn't abide by the same rules as vector. Right, when you zoom in or out with vector, the points shrink or grow, right, depending. But with raster, if something is 100 feet by 100 feet cell size, it is always 100 feet by 100 feet. It doesn't, try to change itself so you can see it as you zoom out. So one of the things that might be helpful is maybe just increasing the cell sizes here, right? So we'll say Folk FA. Very simple. I'm just going to increase in the most immediate neighborhood, and I'm going to say everything take on your maximum value. Right, so what I'm essentially doing here is all these little cells right on the edge here, they're going to become what these values are, right? Because they're much smaller. They're going to take on their maximum. Happens everywhere. I won't use it for any kind of analysis, but I'll have it around in case I need to very quickly and visually. And I'm just going to input the same value that I had previously. Demonstrate to somebody the output of my tool. Now it is much easier to see. Even when I zoom out, now I can have something that I keep, right, at a larger extent to show to a client or to show to a class, and I can very easily classify what these look like, even if I'm not necessarily going to do this for analysis. Right, so that's flow accumulation. Very, very, very cool. Tells you the number of cells that flow into a given cell based on surface of elevation. So if we can do it for every cell, you can also do it for just a few. All right, so where's my little starting point? All right, so I've got these 3 points here. I don't know. Maybe give them each a value of 1 in their ID. In order to be used as an input in this tool, I need to convert them. So I'll go up to convert, go to raster. I'm going to do point to raster. Right, the value field is going to be their FID, right, because I each want them to have a value of 1. Call them raster point. Cell size is all set. There you go. Can't see them, they're real tiny, but if I zoom in, and I looked under the starting point, I'd be able to see a very tiny grid cell. All right. So now I have these 3 grid cells. I'm going to return to the flow accumulation, but now instead of like what I did here, right, every cell flowed their value, so there's obviously going to be times, right, if I use my pixel inspector and went here, right, boop-a-doo-doo-doo, let's get my flow accumulation. Right, there's going to be instances where there's 120,000 cells, right, that come in, or I'll use the regular focal accumulation so it's much easier to see. Right, but look at that. I mean, there's going to be times that 120,579 cells meet here. right, versus a smaller one here, right? Maybe they only have 1761, 1762, and then suddenly, boom, they're in an area where tons of cells are meeting, and because the tons of cells are meeting, right, the value jumps up enormously until it comes down and meets more cells, and so on and so forth. So now instead of every cell getting that value to flow, just these three are going to get that value to flow. So the maximum value I'm ever going to have anywhere is 3. And this allows you, if the other one can see the generalized flow paths, this allows you to very specifically determine if you just dropped something or a number of things, what paths would they take to flow? Oop. What did I mess up there? Oh, I put fill in. That's right, I need my flow accumulation and my flow direction. In my flow direction, need my raster point for my weight. Do that one. And now I get a much cooler thing. Now I'm going to have to zoom in to really see it. Right? Maybe we'll do the thing we did before with the focal statistics so you can really see. Right? Just in your immediate neighborhoods. Take on the maximum value. Totally cosmetic, right? Just doing this so we can see this a little bit easier. And now, starting with these 3 points, right? Let's turn them into these bright red circles. Something really easy to see. Light blue circles. Starting here, each one follows their natural flow path. And in this instance, these two happen to meet here, right? So this would be a flow path taken by 2 of them. So very cool, and something that I want to get you have your brain start thinking beyond just its applications here. Right? If I can start looking at a pathway of how one thing flows, imagine if my surface wasn't elevation, but it was travel time, right? A weird version of travel time, maybe where I allowed the user the opportunity to cross grass, or to cut through buildings, or to do any number of things, and I would increase the amount of time it would take to cross over grass versus a road versus crossing through a building, but I could actually see the best path someone might take. Maybe my surface is wealth or elevation or property value in a city, and I can see the neighborhoods or where wealth would flow, right, within cities based upon that proximity thing. So the point is, when you start to think of flow direction as flowing more than just water, right, you can flow it over a surface of travel time or a surface of wealth or a surface of population density. Those are going to be cool applications that we'll explore to a small degree in another lecture later on something called cost distance.